Okay. Um, I'm going to go through motion in 2 dimensions, kind of a conceptual idea, and then I'm going to end up with 2 sort of example problems that you might see with problems involving motion in 2 dimensions. And the idea is that an object is not moving just right and left, or just up and down, but both at the same time. So let's begin. If an object has a velocity in the y direction straight up and a velocity to the right at the same time, then we know that it has a resultant velocity somewhere between. Notice that blue and red make purple. So we have a velocity that's up and a velocity that's right at the same time, and then we get what's called a resultant velocity. If you've ever played the game Angry Birds, which I know many of you have, the question is gravity programmed in? If it wasn't, then when you pulled it back and shoot the bird, it would fall, or it would go at a straight line forever and never stop, and you wouldn't hit your target. But they have programmed gravity in, and so we know that gravity is going to be pulling down on that object as soon as you let it go. But keep in mind that it's going to be moving right the entire time. So it's moving to the right the entire time. It initially goes up, slows down, stops, and comes back down. So you can hit your target. What we're saying here is that it has 2 velocities at the same time. It has a velocity in the y direction and a velocity in the x direction. Notice that I can slide the blue arrow over to the left, and it's the same height. So what we're going to do here is we're going to combine these 2 velocities. Velocity in the x direction and a velocity in the y direction. Because we can't deal or work with the resultant velocity, we have to separate them out into the x and y components. We also are going to neglect friction due to air resistance. Let's take a look at this cannon that shot a cannonball 6 meters per second to the right. There is no friction due to air resistance, so it's going to go 6 meters per second forever. So for every second, it's going to go 6 meters to the right. That's a 0 gravity path. There's no gravity acting on that ball at all. But if we did turn on gravity, we would notice that that ball is still moving 6 meters to the 6 meters per second to the right. The entire time it's moving 6 meters every second to the right. But initially it had no velocity downward until it came out of the cannon. When it came out of the cannon, notice that the blue downward velocity is increasing by 9.8 meters per second every second. So those are snapshots of an object that has 2 velocities at the same time. Take a photograph taken every 1 second, moving constantly to the right. Same velocity, but increasing by negative 9.8 meters per second every second. So we're dealing with projectile motion with our Angry Bird. We're going to launch it from the ground. We're going to launch it with our resultant velocity, up and to the right. That means that this object will follow a particular path, a trajectory, because it has a y velocity and because it has an x velocity. So what does the path look like? You could trace it with your fingers on the computer screen, and you would know that it's going to go up to an apex, and then it's going to come back down to the ground. Notice that in the second position, the velocity arrow is shrunk. The velocity at the apex vertically is 0, and then the velocity changes directions. It now has a y velocity in the negative direction, and then that velocity is going to grow. So it's shrinking on the way up and growing on the way down because it has a negative acceleration. But also notice that the arrow to the right does not change at all. It will continue moving to the right the entire time. So now we can go back and say, well, the resultant velocity then is a combination of those 2 velocities. At the apex, there is no up velocity, so it is only moving to the right at that moment. Then the resultant velocity comes back down. And if we continued, let's say it didn't hit the ground there to the right, If the path was to continue, it would be farther to the right even, and going faster in the downward direction if it didn't hit the ground. Keep in mind, too, that that velocity to the right is independent of the velocity upward. It does not change. Just because an object is moving up or down does not change the velocity to the right. If you study this diagram that was taken from physicsclassroom.com, the gravity path without gravity is the green, but with gravity is the red. The red one is accelerating, and so it gains more distance with each second. The green one is covering the same ground in each second. And the blue path is the combination of the two. So if you drop a ball, simply drop it, or if you shoot it off to the right with a velocity, either way, they'll be on the ground at the same time. Mythbusters also did a video you can find on YouTube that did the independence of these as well. They actually fired a gun horizontally to the ground, and the bullet hit the ground at the same time it was dropped. But that's only if the velocity is got a horizontal path initially with no angle. Things to remember, excuse me, that the vertical and horizontal motions begin and end at the same time. They share the same time. Vertical and horizontal motions share the same time, but they are independent of each other. They start at the same time and they end at the same time because it's the same object, but they don't affect each other. And I'll show you what I mean in the next couple slides. If a ball is kicked horizontally from the top of a building with a velocity of 6 meters per second, now this 6 meters per second is horizontally, so this ball has been kicked to the right 6 meters per second off a building. And when that happens, the initial velocity vertically is 0 meters per second. Vertically. It does have a horizontal velocity, but it has no vertical velocity initially. And it says, how far from the base of the building will the ball land if the building is 78.4 meters high? Here's the ball. If we just simply drop it, it's going to land on the ground below. The ground is 78.4 meters below where it was dropped. That's why I have a negative 78.4 meter mark there. So if we look at it, it started out at an initial height of 0 meters, and it falls to 78.4 meters. I could calculate every second using the motion equations, equation number 4, which is displacement equals velocity times time, initial velocity times time, plus 1/2 at squared. I can calculate where that ball is each second as it falls. I'm going to take that grid away so we get a good look at that. That ball is gaining more distance in each second. It is accelerating as it falls. It's going 0 meters per second, then it's going 9.8 meters per second, and then 19.6, negative 29.4, and when it impacts the ground, it's going 39.2 meters per second. If I were to give that ball a velocity to the right, no matter what velocity I gave it, it's going to be at the same height every 1 second as it would as if it was simply dropped. The purple ball and the green ball will hit the ground exactly at the same time because the horizontal and vertical velocities are independent of each other. That ball will be gaining the same velocity downward at the same spots. It just happens to be moving to the right as well. Now I could have put 100 meters per second there. It just would be farther to the right when it lands. Or if I put 2 meters per second to the right, it would be closer to the green ball when it lands. Regardless, though, it will be on the ground at the same time. So where would that ball be? Well, if we started out at 0 meters, it's going 6 meters per second as it moves to the right. it takes 4 seconds for that ball to strike the ground. And if it's going 4 seconds, if it's in the air for 4 seconds, we can say average velocity is displacement divided by time, or average velocity times time is displacement. In this case, it would be 6 times 4, or 24 meters. It's 24 meters to the right when it lands. If it was 100 meters per second to the right, then it would be 400 meters to the right. Okay, so let's do one problem here. So our volunteer, Mr. Sticks, is going to come out. Oh, stop it, Mr. Sticks. All right. The ball is thrown 10 meters per second horizontally. So watch him. He's going to throw the ball horizontally only. He's not throwing it up. He's not throwing it down. He's going to throw it straight out to the right. And it goes out and it lands somewhere. The height that he threw it from is 50 meters. So he's standing 50 meters above, or he let it go 50 meters above the ground. I'm asking for the horizontal distance of the ball. In other words, the displacement horizontally. How will we figure that out? We have to separate the horizontal components and the vertical components of the motion. We know that the vertically, it dropped 50 meters, so we have a displacement vertically of negative 50 meters. We also know that the initial velocity vertically is 0, because he didn't throw it down, he didn't throw it up, he threw it horizontally. So when he let it go, gravity took over. We have an acceleration vertically of negative 9.8 meters per second squared. And we know that the horizontal component is 10 meters per second. What is the displacement horizontally? That's what we're looking for. Time is the bridge. Time is the only thing that those two columns have in common. In fact, I drew that vertical line here, and I'm going to tell you that you should not cross that line with any value other than time. It's the only thing that those two items have in common. So let's ask, or let's find the time. We're going to use, and I put it in blue because we're talking about the vertical components here. The displacement equals initial velocity times time plus 1/2 at squared. Negative 50 equals 0 because the initial velocity is 0 times time, so that'll be 0. Half of gravity is negative 4.9 times t squared. So the time it takes that ball to hit the ground is 3.2 seconds, regardless of how fast he threw it outward. But he just happened to throw it 10 meters per second. That means it's 3.2 seconds for each side, because when he let go of the ball, that's when the motion started, horizontally and vertically. When it hits the ground, that's when the motion ends, vertically and horizontally. It's the same time. So now we can just simply use the first basic equation. Velocity is displacement divided by time. Multiply both sides by t, and that's 10 times 3.2, or 32 meters. That ball landed 32 meters away from the building. Okay, you can pause that and kind of digest that if you need. I'm going to go now to a trajectory from the ground to the ground. So this object has been launched from the ground and it lands on the ground. So how are we going to solve that? Well, we're going to do the same thing that we did. We need a horizontal side and a vertical side. And we can deal with this apex. The question, though, before I start, is what is the vertical velocity at the apex? Is it moving up? No. Is it moving down? No. So at the apex, remember, our velocity is 0. What can we say about the time to the apex? We can say that the vertical time to the apex equals the time down. We can also say that the horizontal, the time to get to the apex from the left side, equals the time on the right side, from the apex to the ground. In other words, the time to the apex and the time from the apex are equal. So let's just take a look at an example. If you know the maximum height, A golfer hits a ball during the flight. The ball reaches a maximum height of 20 meters. If the ball is flying at a constant rate of 97 meters per second horizontally, that velocity is to the right, how far does the ball fly? How would I solve that problem? Well, I'm looking for the range. How far did it go to the right? I know it maxed out at 20 meters. That means the apex, right? Isn't the apex the highest point? So what I want to do is I want to just consider from the apex to the end of the flight. So I'm going to erase the first part of this flight as if it never happened for right now. And if I put the ball there, I know it only has a horizontal velocity. It has no up or down velocity. So its velocity there is 0 vertically, but it's moving 97 meters per second to the right. This problem is just like the one we just did. So let's list our vertical components. We know it's going to fall 20 meters, negative 20 meters. It has an initial velocity of 0, a gravity negative 9.8 meters per second squared, and it has a horizontal velocity of 97 meters per second. It's time that we're looking for. You can't cross that line without the time, because that's the only thing they have in common. It's displacement we're searching for after we find the time. Again, we're going to use equation number 4. Motion equation number 4 says displacement equals initial velocity times time plus 1/2 at squared. We plug those values in. The vertical, that's why, excuse me, I made them blue. Half of gravity is negative 4.9, and the displacement is negative 20. The initial velocity is 0. That means the time is 2.02 seconds from the apex, right? Or we could say that's to the apex as well. So we have the time it took to get to the apex, or we could say the time from the apex is 2.02 seconds. Now, in order to bring that over to the horizontal, if we're looking for the total distance, we have to then double that. It's 4.04 seconds for the entire flight. Now we can go back to our initial equation, displacement equals VT. Multiply those two together, and it's 392 meters. It's quite a golf shot. All right. Trig. Chief SOHCAHTOA comes in to help. Sine is opposite over hypotenuse. Cosine adjacent over hypotenuse. Tangent opposite over adjacent. Or a squared plus b squared equals c squared. Now, if you want to pause this at any point, you may do so. But all I'm doing here is showing you how to find the vector components of a resultant velocity. But it's just basic review for trig. So you can pause it and digest that if you need. I'm going to go ahead and put it to use in just a second anyway. So here we go. Combining horizontal and vertical velocities as vectors. If you have a ball and you give it a y velocity and an x velocity, we can combine the y velocity and x velocity to give us the resultant velocity, which I had mentioned before. But I want to make a triangle out of that. How am I going to do that? I can simply slide the y over that direction, tip to tail, they call that. So if I know the hypotenuse of that 90-degree angle, I can find the y value and the x value if I'm given the angle, one of the other angles. So let's try it. Find the v and the vx and the vy, the vertical and the horizontal velocities, if you are shooting an object 100 meters per second at an angle of 30 degrees. So we're looking for the x and the y. So I draw it first, and I try to draw it. I'm not using a protractor, but I know that's about 90. I know that's 90 degrees, and I know that's about 45. So I know a 30-degree angle looks something like that. So I'm going to erase that. And you can jot that down in your notes. You got a 30-degree angle, and we can make our triangle. It's the Vx and Vy that we're searching for. And we're given the resultant velocity of 100 meters per second, and that's our hypotenuse. Sine of 30 degrees is y, because it's the opposite, over 100. So y is 50. Cosine, it'll be the x velocity. So it's cosine of 30 times 100 is 86.6 meters per second. If you need to, pause it and see if you get the same numbers as I do. Make sure your calculator is on degrees and not radians. So I'm just going to slide that velocity over there to the left. That means that that ball is moving up initially 50 meters per second and to the right 86.6 meters per second. Now I'm going to ask you these two questions. A projectile is launched with a velocity of 210 meters per second at an angle of 40 degrees. What is the range? That is the horizontal distance. And what is the maximum height of the motion? So here is a diagram of that motion. And there's 90 degrees, so that's about 40 degrees. And our hypotenuse, or our resultant velocity, is 210 meters per second. We're looking for the range. The range is the horizontal displacement. How far did it go to the right? That's what I'm looking for. First, we have to separate them into their components. So I redraw it as a triangle. The sine of 40 times 210 gives me 135. Cosine of 40 times 210 gives me 161 meters per second, about. That means that ball is moving up with a velocity of 135 meters per second, and it's moving to the right 161 meters per second. So we're going to now make a table and start listing our horizontal and vertical components. The velocity to the right, we said, was 161 meters per second. Our velocity up was 135 meters per second. Keep in mind that we are neglecting friction due to air resistance. It's minimal on our projectile. We know gravity is acting on the vertical side. And we know the velocity at the apex is 0 meters per second, vertically only. It is moving to the right still, 161, but it's not moving up or down. And I'm only working right now with the vertical components. So I need the time. I want to know how long that projectile is in the air. That way I can find the displacement. How high did it go vertically? I'm looking for the time the thing is in the air so I can find its horizontal displacement. Those are the two questions, right? The displacement vertically and the displacement horizontally. Let's find the time to the apex first. You have an equation that says that the acceleration is the change in velocity over time. I give the equation as VF equals VI plus AT. So you can plug in those values. I did it blue. I put that in blue so that you know we're only working with the vertical components right now, looking for how long it's in the air. 0 final velocity at the apex, 135 meters per second straight up initially. We know acceleration is negative 9.8 meters per second squared. So we can solve for t. In this case, it takes 13.8 seconds to reach the apex. 13.8 seconds to get to the apex. So what does that say about the time the object is in flight? (27.6 seconds up and then back down. It's double. So 13.8 times 2. That's the time I can bring to the horizontal side, because I'm looking for the whole range from the beginning to the end of the flight. So let's find our horizontal components first. Now that we have the total time for the entire motion, we can find the range using the first equation, because there's no acceleration. It's just v equals displacement divided by time. So it's 161 meters per second to the right for a time of 27.6 seconds. That gives us a number about 4,444 meters. That is our displacement to the right. Half the problem is solved. Now, let's find the maximum height of the projectile. That means that the distance it went from the ground to the apex. And we can use equation number 4, displacement equals VIT plus 1/2 AT squared. Displacement is 135 meters per second. That's our initial velocity upward. And notice we're using 13.8 seconds now, because that's the time to the apex. I've already multiplied the gravity by a half. That's where I got negative 4.9. That's half of 9.8. And then 13.8 is, again, the time, and we got to square that. When you do that, you get 930 meters in the air. That ball is 930 meters in the air. So the point of that is that you have to separate out the vertical and the horizontal velocities first, and that they are independent of each other. So once you draw that line in making that table, once you draw this line, the only thing that goes from this side to this side is time. That's the only thing they have in common, time. And we had to double this to get the entire time of the motion. That's the time from here to here. The time to here was 13.8. The entire time was 27.6.